All right, so in this video lecture, we're going to go over a worksheet, worksheet 22 here. This is on Schoology in the week 17 folder, or in whatever folder that we're currently on. But I didn't give you guys a hard copy, but that's okay. So if you want to look at the original copy, you can. If you don't care to, that's fine. You can just write all these notes on a separate sheet of paper. We're going to start here on problem number 2. The other side has just free body diagrams. That is problem number 1. We're not worried about that. We're just going to go right for problem number 2 here. And it says a 4 kilogram mass is sitting at rest on top of a coil. Spring is shown to the right. What will be the weight of the 4 kilogram mass? How much upward force will be exerted on the mass by the spring? So in this question, we're always going to redraw. Even though they give us these diagrams, and you can see them all the pictures on this page, we always want to redraw. It just helps make the problem more our own, and then we know everything that's currently there. So we have a mass sitting on a spring. There's some kind of platform, I think, here. All right, something like that. And it's just sitting there. So it was set on there, and it's just and it's able to rest right on the spring. The spring is compressed, and we get something like this. So okay, you get the idea. All right, so let's go ahead and draw it. In all of our problems here, we're going to start with a free body diagram. I think they said the first thing to find out here is what will the weight be. But let's always start by drawing the situation and then a free body diagram. So with the free body diagram, we draw a dot in the center of our object, which is the mass. That is the object we're interested in, not the spring, not the platform, just the mass at the top. There are 2 forces on this mass. One is the force of gravity, and it points straight down. The other is, you might want to say tension because it involves kind of like a rope or a spring, but we want to use force spring here. Or you might want to use, probably the more likely one than tension, is normal. You might have wanted to say normal. I don't like normal here because we can be more specific than that. The surface that is returning the normal force is a spring, so let's use force spring. That's why. Okay, so we have this right here going on. There are no other forces going on here. There's no normal force because the normal force is the force spring. We just called it force spring to be a little more exact. Normal force is always just whatever the surface returns, right? The returning force from the surface. So that is force spring. All right, so this is what we have. When we, after we do the free body diagram, which is right there, the next thing we do is we sum our forces in a direction. This is the same as writing Newton's second law. And the only direction we're interested in here is the y direction. So we sum our forces in the y direction just like that. We write sigma Fy equals MAY. Okay, then we assign a coordinate axis. So we have to decide, what does up and down in the y direction mean? And we'll just stick with what it normally means, which is up is positive y and down is negative y. So we'll write that in. That's just our coordinate system. If you want to write the x direction in, you can as well, but I don't think we need to. So this tells us that when we sum our forces or add these y forces, force spring and force gravity, that they're going to have signs, right? Positive or negative. Force spring will get the positive sign because it points up, and force gravity the negative sign because it points down. So when we write them in our equation, we write them like this. Force spring being positive, force gravity being negative. Then we multiply by the mass of the block. And I think in the problem they told us the mass of the block. Let's go back and look really quick. It says here it's 4 kilogram mass. So we want to know what its weight is the first thing they ask us. All right, so if we know the mass is 4 kilograms, I'm going to go ahead and write it. Oh, I'll have to pause this video really quick. All right, sorry about that. I'm at the school, so I had to take it. I thought it might be a parent or a teacher or somebody calling, but it was actually just I don't know, some random call that I didn't, and no one I wanted to talk to. All right, so anyways, this is what we have here, and the acceleration. Is this object accelerating right now? Is it speeding up into the ground or up into the air? You might say it wants to speed up into the ground, right, because of gravity, but it's not, because there's no net acceleration, right? The acceleration down is canceled by the acceleration from the surface up, and there's no net acceleration, so this is actually 0. All right, and what we can see from this is that 4 times 0 is just going to equal 0. So on the left side, we'll still have force spring minus force gravity. So hopefully you're getting used to that, right? That FSP means force spring, and FG means force gravity. All right, by finishing this equation, we can go ahead and add this FG over the other side. We can learn something. Notice I haven't even tried to figure out what the problem is asking, right? I'm just kind of working in the y direction off this Newton's second law formula, right? Just seeing what I can figure out even before I even deal with the problem, almost in a way. So I can see that force spring is force gravity. Okay. So what does the question ask? Well, they ask us, what is the object's weight? And weight is on the screen right now. We can see another way of saying weight in physics class. So what would that be? Well, we learned that weight is equal to Fg, the force of gravity. Fg is always equal to mg. And we have to be careful here, because this g is telling us the word gravity. It is a descriptor, a subscript. Let me erase that little, ooh. That looks better. All right, and this g is telling us the acceleration due to gravity on the planet Earth. So it's the gravitational field on Earth is really what it is. And this one is 9.81. All right, so that's kind of what we're working with here. So we can find the weight fairly easily, right? We just multiply m by baby g, right? If we multiply these two, we get the weight. So weight then, or Fg, right? I'm just going to call it Fg because weight is the same as Fg, right? I'm going to say Fg then, the weight, is equal to the mass, which is 4 kilograms, times 9.81 meters per second squared. It's an acceleration. 4 times 9.81, that's where I need my calculator. I'd be guessing, give me 1 second. Oh, where is that calculator? And you think I'd have it right there. It seems like I always have it right there. I got one right here though. All right, 39.24. Units are newtons, named after Sir Isaac Newton. And this, once again, Fg is the same as weight. Now that changes, like your weight or this object's weight can change on a different planet because baby G for a different planet is different. But your mass or the crate's mass, the 4, will be the same regardless of the planet. But the orange part will change based on the planet. If you were on the moon, like I said before, I think this is about 1.6. So it's going to be a lot less on the moon. I think about 1/6 actually of 9.81. All right, so there we go. This is our answer to part A. So this is 2A, and this is our answer right here. All right, 39.24 newtons, the weight. So if you want, I can put a yellow box around it. All right, going back to part B. The first one was how much weight. Part B, how much upward force will be exerted on this mass by the spring? So we want to know what the force of the spring is. Well, if we just look at the work we did, we can see right here that force spring, let me grab this orange highlighter, force spring is equal to force gravity. So if we know force gravity, we know force spring. And we just so happen to know force gravity, right? We just solved it a second ago. So this force gravity, this 39.24, can now, we can bring it down here and plug it into this equation. And now we can see the answer to the force spring is 39.24 newtons. If you want, I can put a yellow box around that too. And that's it. All right, let's go ahead and go to problem 2. I probably am going to get another sheet of paper here. Okay. So in problem 3. In problem 3, they say a crate which has a mass of 55 kilograms is being lifted straight up by a rope at a constant speed. What will be the tension in the rope? Okay, so we have something, we have a problem that deals with tension, first of all. So we'll have to talk about what that is. So we have a crate attached to a rope. Now we don't know my drawing of a 3-dimensional crate, or 2-dimensional, or however I'm trying to draw this, is not very good. All right, so we got some crate sitting here. I should really step up my drawing game. That's a little bit better. Okay, so we have this crate attached to this rope, and it's moving up. But in the drawing itself, you're not going to be able to tell it's moving up. So we're going to have to add that. So that's something I mentioned before, that free body diagrams like this, which we're about to draw, do not show motion. So even though this is moving up, it won't be obvious unless we note it, right? Unless we make a little note there saying, oh, by the way, it's moving up at a constant speed. The mass is equal to 55. I usually just like to write a note somewhere on there just saying that. So once again, there's two forces. And once again, there's no normal force. Here's why. We have an upwards force and we have a downwards force. Everyone should know the downwards force. That is force gravity. The upwards force, though, is not normal. Normal force requires a surface to push back on the crate, but that isn't the case here, right? The crate is being pulled up by a rope, and there's no surface, right? So this force pulling upwards, we like to call it, instead of calling it the force of the rope, we like to call it T for tension. So that's what this T means. I can write the word for you. I'll just make a little note here. This means tension. So whenever we have a pulling force in a rope, it is called tension. And tension never pushes, right? You ever seen a rope push something? No, that's absurd. All right, so we have these two forces here that we're dealing with. And we're going to do the problem the same way. I don't even know what the problem is asking yet, but I guarantee we draw the free body diagram that the next step, what we're going to do is sum the forces, right? and in the y direction. Why in the y direction? Because that's all we know. That's all we care about. There's nothing going on in the x direction. There are no x forces. So I can go ahead and write positive y and negative y for my y direction, right? This is my coordinate axis system that I'm going to work with here. And I can start summing these forces. So let's write it right over here. Sigma Fy equals MAY. Our positive y force is going to be, should be apparent, points up is tension, and our negative y force is force gravity, and it points down. So let's go ahead and write that. Tension will get the positive sign, and force gravity will get the negative sign. You might say, well, if we summed it, why are you subtracting it, right? Sum means add. Because really, what this was t plus negative Fg. And that's the same as t minus Fg. So it's just easier for me to write t minus Fg. So that's why. The mass of the crate we said was 55. And what about this acceleration, right? Because you could speed up the crate, you could pull it up as hard as you want, right? But they tell us that it's not speeding up. They tell us that the velocity is upwards, right? V, but it's not changing, right? It's just staying the same. So this V that points upwards, we don't know what it is. It could be 100 miles an hour. It could be 10 miles an hour. What we do know about it is it's constant. We know it's not changing. All right. And if it's constant and it's not changing, then we know the acceleration is equal to 0. It's not speeding up. It's not slowing down. That's what acceleration is. It has the weird units of meters per second squared, sure, but what it means is your change in speed. Is the object speeding up? Is it slowing down? If no, then acceleration is 0. All right. So we can multiply the right side, get 0. Once again, work with some variables here, which is kind of awkward or kind of, maybe something you're not used to, but it's not bad. Just treat them like numbers. Push Fg to the other side by adding it. Cancel it here. Rewrite what's left. We have a T over here still. Have an Fg over here. All right. So we didn't get an answer for what the tension in the rope is. Exact answer. We have an answer, right? We know that tension is force gravity. Now, what is it exactly? Well, it depends on what force gravity is. So let's go back and look at the problem. It says, problem number 3, a crate which has a mass of 55 kilograms is being lifted straight up by a rope at a constant speed. What will be the tension in the rope? All right, so I didn't label this, so I should probably do that right now. This is number 3. I usually like to label the problems. Maybe do the same with this one up here. Just so when you go back and look at your notes, you don't forget where that problem came from. This is problem 2. This was our answer to 2B down here, by the way. So if you want to write that in, you can. Okay. So what would be the tension in the rope? Well, we just learned tension is Fg. And if we remember a second ago, we said that Fg is what formula? Hopefully you remember this. Mg. And that's our formula for force gravity. Fg is mg. So let's go ahead and plug in our values. The mass is 55 kilograms. And baby G is 9.81. Once again here, our units are going to be newtons. I'm not sure what this is going to be, so we better get our calculator. I'm seeing about 539.55. newtons. Once again, I can put a yellow box around it, make it something you'll remember. All right, so there we go. Units are newtons, and we are good to go. Let's go ahead and go to problem 4. Problem 4 says a crate which has a mass of 55 kilograms is being pushed along a horizontal surface. Let me read that one more time. A crate which has a mass of 55 kilograms is being pushed along a horizontal surface crate. I'm not sure. It looks to me like that's a typo. That word crate shouldn't be there a second time. This is awkward to read. So let's read it again. A crate which has a mass of 55 kilograms being pushed along a horizontal surface by a force of 85.0 newtons, so that the crate is moving to the left at a constant speed. Complete the free body diagram showing all the forces acting on the crate. What will be the magnitude of the normal force? What will be the magnitude of the gravitational force acting on the crate? And how much frictional force, will be acting on the crate as it is pushed along the surface at a constant speed. All right, so something to notice here. This is why we redraw, right? We don't draw our force to the left on the right side. I don't know why they would do this, but this is not okay for a free body diagram. This is just a sketch, so it's okay for a sketch, but a free body diagram is drawn a certain way. So let's draw a free body diagram the right way. I'm going to grab another sheet of paper here. All right, so we'll call the mass M again. And it's being pushed along a surface. And so for our free body diagram, let's go ahead and draw our dot in the center. Probably should draw our surface or attempt to draw it. I don't know, something like that, right? And it's being pushed to the left. And they also tell us that it's being pushed at a constant speed. Now there is going to be frictional force. And here's why. If we push something at a constant speed, to the left, if there's some V that's constant, and it's not speeding up, right? Like if this is happening, that there's a push going to the left. Forces mean accelerations. Then that would mean there's acceleration to the left. And therefore this object would speed up to the left. But it's not speeding up, right? They tell us it's a constant speed. So in order for it to be constant, there has to be a kinetic frictional force this direction. Why kinetic? Because it's moving. So I'm going to put that little K there after FFR. There are also two more forces here, just like last time. Or I shouldn't say last time, maybe just like in the lab. Whoops, my eraser came on. All right, so we'll call this force gravity. And we'll call this upwards force normal. I'm going to use lowercase n just because it doesn't look like uppercase N, which is Newton. You can use uppercase N there, but it just, I don't know. It's nicer sometimes using lowercase n. So we have something like this. And the first problem says complete the free body diagram, showing all the forces acting on the crate. So this is our answer to part A. I think this is question 4. So this free body diagram is our answer to 4A. Okay. So then 4B says, what will be the magnitude of the normal force acting on this crate? If we look at this, we can see normal force points 90 degrees to the surface, straight up in this case. Not always straight up, right? It doesn't have to be, but it is in this case. So if we want to know about normal force, we're going to need to work in the y direction. So we'll go ahead and draw a coordinate axis. I'm going to call up positive y, down negative y. I'm going to call right positive x, and left negative x. I'm then going to sum my forces in the y direction because normal force is in the y direction. So let's go ahead and write that. Okay, so we'll go ahead and put the forces into the sigma, right? Because we're summing them or adding them. Force N is up, so it's positive. Force gravity is down, so it's negative. Friction and push don't get put in here because they're X forces, right? They point right and left. We only want vertical forces, up and down. So then we have the mass of the block. I think they tell us that this is a 55 kilogram block. I should go check. I don't think they do. I don't think they tell us oh no, they do tell us the mass. Yeah, it is 55. I'm sorry. Geez, I'm skipping over it reading about the 85 newtons. All right, so I'm going to go ahead and write that right there. And we also know something about the push. And I want to write that down. That's what I was distracted by. This force push is 85 newtons. So we do know a little bit more than maybe I realized there. That's okay. It's not going to change what we've done so far. We just wanted to know if there was a mass. So that mass is 55 kilograms. So I'm going to go ahead and write that in this equation. And then once again, is the object accelerating or speeding up into the air or into the surface? And you'd be like, no, that's ridiculous. It's not speeding up into the air or into the surface. So this is 0. Because that's true, the right side is 0. And you can see that we are going to be able to say something here. That we can add FG to this side and add FG to this side and get that force normal is equal to force gravity. Now this doesn't solve anything for us, I don't think, right? Not yet. But it moves us along the right path, right? Because we want to know what force normal is. I think that was where they wanted us to start. Yeah, for part B, what is the magnitude of the normal force acting on this crate? For part B. Okay, so normal force we're seeing right here is equal to Fg. And Fg is always, regardless of angle or whatever, is mg. So we'll go ahead and plug in what we know. I think this is going to look familiar. It should look familiar to you. We just saw this in the last problem. And we saw that force gravity was equal to 539. .55 newtons. And so therefore force normal is equal to 539.55 newtons. All right. So there we have it. That's the answer to, this is number 4, B. All right, so now we want to move on to force C. Number 4, part C says, what will be the magnitude of the gravitational force acting on the crate? The magnitude of the gravitational force acting on the crate. I think we already answered this, right? We said that force normal is force gravity. Then we went ahead and solved for force gravity. So the answer to part C is just going to be this, very similar, right, to what we wrote for part 4B, but it's just going to be that force gravity, since this is true right here, that normal equals gravity, then gravity has to equal 539.55 newtons. Whoa, an eraser is doing too much work. 539.55. I don't know why that's hard for me to read. I'm going to write it one more time. Okay, 539.55 newtons. Just trying to make this look a little bit better. End up erasing most of my problem. Put some yellow highlighter around it for our answer. And this is part, I think this is number 4C. That's what we said. Yeah, okay. So then let's go to the last one, which is 4D. How much frictional force will be acting on the crate as it is pushed along the horizontal surface at a constant speed? Okay, so frictional force is going to come from the x direction. And so let's start the same way we did with the y direction, right, which was sigma Fy equals may. So you can see Newton's second law being very important here in the y direction. Let's do the same thing in the x direction. All right, if we go back down here, we can look at this. We should probably look at this. This is much nicer. We already have all our forces labeled. We called left negative, right? In the negative x direction, and right the positive x direction. So in the negative x direction, we have force push, and in the positive right direction, we have force friction. So it looks to me like, we'll go ahead and put them into the sigma part. We'll have force friction kinetic, which is positive, minus the force of the push. So we're really adding a negative there. So subtracting is the same as adding a negative. The mass is equal to, did they tell us that? I don't think it's 55 this time. I think it's something different. No, we're still on the same problem. Jeez. So I'm starting to get tired here. Sorry about that. Thinking we're on a new problem, and it's still that same 55 kilogram crate. All right, then. Let's go ahead and add that in. Now, what is the acceleration in the x direction? They told us that it's moving at a constant speed, not speeding up or slowing down as it's being pushed to the left. So if that's the case, it's moving left at a constant speed. It is not accelerating. 55 times 0 is just 0. And we can see that force friction kinetic is equal to force push. All right. So if we know the pushing force, we know friction kinetic. And it just so happens that they tell us the force of the push, right? They tell us that that force is equal to 85 newtons. So let's go ahead and write that in. And there's our answer for part 4D. All right. So sometimes we have to use the relationship from the lab where we said force friction equals mu Fn, but sometimes we don't, right? We didn't need to know mu here. Yeah, we didn't even need to know the normal force. And we were able to solve for force friction kinetic. Okay. Let's see. I'm going to check the time and maybe we'll add one more on. Maybe we won't.